Now we're going to introduce you to something called a combustion analysis. Combustion analysis is a way to identify the empirical formula by combusting an organic compound. Do you remember what an organic compound is, Fred?
It's a compound that contains carbon and hydrogen.
That's right. Compound that contains carbon and hydrogen. It can have other stuff like oxygen or sulfur or nitrogen in it as well, but it predominantly contains carbon or hydrogen. All right. And when you combust something that contains carbon and hydrogen, so like CXHY, maybe OZ, right? You combine that with oxygen. That's what combustion means. And what are the products of a combustion reaction, Fred?
Carbon dioxide and water.
That's right. Carbon dioxide and water are our products for that sort of a reaction. And so what we do in a combustion reaction is, because there's only carbon dioxide and water produced, we collect the amount of water through so we perform the reaction here with plenty of oxygen, and we drive the oxygen or the products and the oxygen through here, and the water that results is absorbed by one material and the carbon dioxide is absorbed by another. And the result is the change in the mass of these two substances can tell us what the amount of carbon and hydrogen was in that sample that we combusted. Okay, and that's because all this carbon ends up as carbon dioxide, and all of this hydrogen ends up as water. Okay, so it's a convenient way to determine the amount, the moles. We can relate the amount in mass of carbon dioxide to the mass of this, or moles of carbon, and the mass of water to the moles of hydrogen. And then after we have the moles of carbon and moles of hydrogen, we have the empirical ratio, the empirical formula. To get oxygen, you often just subtract the mass of carbon and hydrogen from the mass of the initial sample, and we'll go over that as an example. Okay, so here's a combustion reaction. We take 5.217 gram sample, and it contained carbon, hydrogen, and oxygen, and it resulted in 7.406 grams of carbon dioxide and that much water, and then we can calculate the empirical formula. Now again, the empirical formula is CXHYOZ. We want these moles, right? That's what empirical formula is, moles of carbon, hydrogen, and oxygen. Okay, so to do that, I can start with so I want moles of, we'll start off with moles of carbon, and we start off, or we utilize our 7.406 grams of carbon dioxide, all right, and we can relate it to that moles of carbon, because grams of carbon dioxide goes to moles of carbon dioxide, right? There's grams of carbon dioxide goes to moles of carbon dioxide, that's right. And there's 44 grams per mole, and then I can go from moles of carbon dioxide to moles of carbon. So for every mole of carbon dioxide, I get 1 mole of carbon. Okay? So 7.406 divided by 44 relates the moles, or identifies the moles of carbon, 0.168. I can repeat that with moles of water. All right. Maybe give myself a little bit more space. All right, moles of water. Starting off with what this time?
Grams of water.
That's right. Actually, I don't want moles of water. I want what?
Moles of hydrogen.
Yeah, you want moles of hydrogen over here. Right? Because that's what I want for my empirical formula. So if I start off with my grams of water, 4.512, and I go from grams of water to moles of water, and then I can go from moles of water to moles of hydrogen.
Yeah, it's just 2.
That's right. There's 2 moles of hydrogen for every 1 mole of water. And so that can give me, again, what I'm after over here, which is moles of hydrogen. Okay, so 4.512 divided by, there's 18 grams for every mole, right? Divided by 18 gives me moles of water, and then times 2 gives me moles of hydrogen, so 0.501. So what that does is that gives us the C 0.168 and H 0.501. Oxygen, we still don't know.
How do you get the oxygen?
Well, we can get the oxygen by looking at the resulting mass from the initial 5.217 gram sample that we started with. So if I have 5.217 grams of sample, if I subtract the grams of carbon and subtract the grams of hydrogen, what will be left is the grams of oxygen. Okay?
Do we have the grams of carbon?
We don't have the grams of carbon, but we do have the moles of carbon, 0.168. So I can get the grams of carbon by taking 0.168 moles of carbon and going from moles of carbon to grams of carbon. So 12 grams is 1 mole. So 0.168 times 12, I got 2.016 grams of carbon. I can do the same thing with hydrogen, 0.501 moles of hydrogen. And I want to go to grams of hydrogen now to subtract it from the sample. 1 mole of hydrogen is 1 gram of hydrogen, close enough, usually, right? So 0.501 grams of hydrogen. So now I go grams of sample, 5.217, minus the grams of carbon, 2.016, minus 0.501. And what's that value?
Well, that's too high.
Oh, I made a mistake. What did I do? I did times there. Okay, try again. 5.217 minus 2.016 minus 0.501. So 2.7 grams of oxygen. And then that 2.7 grams of oxygen, I can convert to moles of oxygen, right?
And you want to go to moles to get the empirical formula?
That's right. So 2.7 divided by 16, there's 16 grams for every mole. So 0.169 grams, moles of oxygen. So I use that up here, 0.169. So to drive these to 0, I divide them all by the smallest value. At least some of them are going to try to drive them to 1. 168.
Divide by the lowest number.
That's right. Okay, so that gives me C, 1, H, what's 0.5 divided by 0.168?
0.501.
So it looks like it's going to be 3. C, H3O. Okay, good. So I got the empirical formula by looking at the moles of the carbon, moles of hydrogen, and then converting that to grams of carbon, grams of hydrogen, and finding the grams of oxygen and converting that to moles. Okay. Yep, that's it. So here's another one for you to practice. Last chance to do a combustion practice here. So everybody at home, you take a chance, follow the model back up if you need to follow the model and perform it for yourself. All right. Okay, Fred, what should we do here?
We need to find moles of carbon and hydrogen and sulfur.
That's right. We need our empirical formula, CXHYSZ.
So start with grams of carbon dioxide and go to moles of carbon.
Okay, so 9.377 grams of carbon dioxide, and I want to go to moles of carbon. I go from grams of carbon dioxide to moles of carbon dioxide, and then moles of carbon dioxide to moles of carbon, which is a 1-to-1 ratio, 44. So 9.377 divided by 44. 0.213 moles of carbon. Okay, and then I do the same thing for the what?
Hydrogen, the water.
All right, so I want moles of hydrogen, and I start off with 1.59 grams of water. 18 grams of water for every 1 mole. And then 1 mole of water gives me 2 moles of hydrogen. So 1.59 divided by 18 times 2, 0.176. So I got C, 0.213, H, 0.176. Okay. Now how do I get sulfur?
We need to take the mass of the sample and subtract the mass of the carbon and hydrogen.
All right, so I have the moles of the carbon and hydrogen, and I need to get the grams now of carbon and grams of hydrogen. So for every 1 mole of carbon, that's 12 grams of carbon. For every 1 mole of hydrogen, that's 1 gram of hydrogen. So this is 0.176, but 12 times 0.213, that's 2.556. So there are my grams of my carbon and my hydrogen, right? And now I take 3.88, because that's what?
Grams of sample.
That's grams of sample. And I subtract my 2.556 grams of carbon and my 0.176 grams of hydrogen. And the rest must be what?
Grams of sulfur.
Okay, so 3.88 minus 2.556, 2.556 minus 0.176. Whoops. Okay, so I got 1.148 grams of hydrogen, or sulfur, and I'm going to convert that grams of sulfur to what?
Moles.
Yeah, there's 32 grams for every 1 mole. Whoops. Yeah, I want to get it to moles of sulfur. So 1.148 divided by 32, so that's sulfur 0.0359. So sulfur is the smallest, so I'm going to have to divide everything by the sulfur, 0.0359. So 0.213 divided by that value there, that gives us C6, 0.176 divided by my sulfur there, H5, and then sulfur is the 1. So C6H5 1. C6H51. So there it is. Hey. Okay, good job. We got the empirical formula by looking at the combustion analysis. Excellent work.